you will find on my website. And I would be glad to discuss individually or in groups with you those parts of the presentation that I've been forced to skip. So we saw that in order for a basis set to be of any use, it should allow you to calculate easily the action of the Hamiltonian over a wave function. Right? So a Hamiltonian is made of a kinetic energy part and a potential energy part. The way the kinetic energy part in plane waves is calculated is in reciprocal space. So you basically take the Fourier coefficient of the wave function, you multiply it by the square modulus of the wave vector, and you're done. As for the kinetic energy, the potential energy part, this is calculated more easily in real space. So if you calculate first the action of V over U, and then, if needed, you calculate back the Fourier coefficients by Fourier transform. You have to calculate the density in order to do the self-consistent, to close the self-consistent cycle, and this again is easily done in real space. The exchange correlation potential is trivially calculated in real space because this is a function of the local density, or in more sophisticated approaches such as the GGA of the local density and its gradients. The Hartree potential is the electrostatic potential generated by a classical charge distribution rho of R prime that has the form of this convolution. That is more easily calculated in reciprocal space because in reciprocal space this convolution is just a product. So you take the Fourier transform of this and you get the product of the Fourier transform of rho, that is rho tilde, times the Fourier transform of 1 over R, that is 4 pi over G squared. So I will skip the comment on why plane waves are great, and just a few words on what is bad about plane waves. That is the fact that they have a uniform spatial resolution, whereas in atoms you need a larger spatial resolution near the nucleus than far from it, right? So in atoms all over the periodic table, the 1s energy, 1 electron energy, scale as the square of the atomic number. This is just the 1s energy of a nitrogen atom with charge Z. The corresponding Bohr radius scales as 1 over Z, right? But the kinetic energy cutoff necessary to describe a wave function that has this special extent or this large kinetic energy scales quadratically with the kinetic with the atomic number. If you make a back of an envelope calculation and you want to calculate what is the number of plane waves whose kinetic energy is smaller than z square, then what is z square? Z square would be the square of the radius of a sphere that would enclose all these plane waves. So this is the square of the radius. The number of plane waves is proportional to the volume of this sphere. so it would be proportional to the cube of the atomic number. However, chemical properties are more determined, much more determined, by the ionization potential of an atom than of its 1s eigenvalue that may have energies of kilovolts or tens of kilovolts. And this ionization potential, of course, it oscillates across the periodic table. It shows periodicity, hence the name of periodic table, but as an order of magnitude, it does not depend on Z. It does not show this Z square dependence. So both the ionization potential and the typical size of an atom are independent of the atomic number, whereas the description of this atom using plane waves would require a numerical effort that a number of plane waves that scales cubically with the number with the atomic number. Here we have a problem with what, with a joke, we can call the first principle of computational physics, that states more or less that when two systems have similar physical and chemical properties, their simulation should require a similar amount of computer resources. Take, for instance, two atoms whose chemistry is not so different, not the same, but not so different either. Say germanium and silicon. They have the same number of valence electrons, they crystallize in the same crystal structure, they have very similar properties. Still, because of this dependence of the number of plane waves of the 1s of the core states, the description of silicon and germanium using plane waves would require a totally different amount of computer resources. All for describing core states in silicon and germanium that have little, if any, chemical relevance. So we have to imagine a way to treat silicon and germanium with a similar amount of computer resources. And the way is the notion of pseudo-atoms and pseudo-potentials. So imagine pseudo-atoms whose chemical properties are very similar to those of real atoms, but whose pseudo-potentials are as gentle as possible. So no deep potential that would bind the core states. Those pseudo-potentials have the property of binding only the valence states that are more or less independent of the atomic number. Of course, they are not independent of the atomic number, but they are not as dramatically dependent of the atomic number as core states are. So basically, the property of pseudopotentials that the pseudopotentials have to fulfill is that they do not have core states. For any given valence states of any given angular symmetry are the lowest lying states of that symmetry. Being the low lying states, those orbitals are nodeless and smooth. And in order to reproduce the chemical properties of the system as well as possible, the pseudo energies should be equal to the all electron energies in the valence region, and the wave function of the pseudo wave function should coincide with the all electron wave function outside of the core region. Why? Because the square modulus of the wave function is the contribution of that orbital to the charge density. The charge density is what determines the chemical bonding, and so the pseudo potential must describe the chemical bonds at its best. Hence, therefore, the valence orbitals for the pseudo potential must coincide with the valence orbitals for the all electron potential. by imposing the equality of energies and orbitals outside some core radius, and by forcing the form of the pseudo-potential of the pseudo-wave function inside the core radius in such a way that the pseudo-wave function is nodeless and as smooth as possible, we can invert the Schrödinger equation from the knowledge of the pseudo-wave function that is guessed by us. So we guess the wave function by the condition that it coincides with the all-electron wave function. This is the all-electron wave function, the 3s for silicon, that has two nodes, and you see that beyond this core radius the two coincide, and inside the core radius the pseudo wave function is nodeless, whereas the all-electron wave function has nodes. By inverting the one-electron Schrödinger equation for this 3s pseudo-orbital, we could find the pseudo-potential that has this 3s pseudo-wave function as its ground state. We repeat the procedure for the 3p state that has just one node in this case, and no nodes in for pseudo-potential. And for the 3D state has no nodes in the first place, even with all electrons, and the correction of introduced by pseudization, by pseudizing the wave function, because there is no nodes to correct, is in this case very minor. This is the procedure that is followed for so-called norm-conserving pseudopotentials that have the nasty property of requiring very many wave functions for some elements, particularly transition metal elements. And more generally, I would say, but let me stop here, for some elements. And on Saturday, you will learn from Andrea Dal Corso how a new class of pseudopotentials can be generated in such a way that the pseudo wave function, in this case for copper, is made smoother than the rather hard pseudo wave function that would be generated for norm-conserving pseudopotentials, at the price of violating the norm conservation. So essentially here we have the norm of the pseudo-wave function that does not equal 1, it is something different, and because of this violation of the norm conservation, the one-electron Schrödinger equation is not of the usual form, but it is of a generalized form where you have an overlap matrix on the right-hand side that takes into account the missing charge in the reconstruction process. But I will stop it here and will refer to Andrea's course lecture on Saturday morning. So we have seen before that in order to apply the Hamiltonian to wave functions expanded in plane waves, and in order to solve the Schrödinger the Poisson equation for calculating the Hartree potential, one has to do Fourier transforms for passing from real space here to reciprocal space. And basically what one does numerically this integral, and we slices the real space in a homogeneous grid along 3 axes, A1, A2, and A3, that are the crystallographic axis, and you basically map this continuous integral into a discrete sum, and vice versa. All the trick of the fast Fourier transform comes from the fact that in any crystal structure, the reciprocal lattice vectors are dual to the direct lattice vector, in the sense that the product of G1 times A1 is equal to 2 pi, but G1 times A2 or A3 is equal to 0. So the scalar product of this direct space vector times this reciprocal space vector is basically the sum of the products of these integer numbers. So basically you map this seemingly rather complicated integral into a standard operation where you have a three-dimensional array that you combine with a face. I think there is a missing n here at the denominator, where you have products of these integer numbers. And this fast Fourier transform algorithm is devised, is a very clever algorithm that allows you to calculate this transform in a computer time that is proportional to the product of the number of terms, of the number of elements, times its logarithm. It seems magic, because here basically you have to calculate a number of integrals that is equal to the number of points. But the integral requires a number of operations that is also equal to the number of points. So in order to calculate all of these integrals, if you do this the stupid way, the way I would do it, that would require a computer time proportional to the square of the number of points. Instead, because of this very clever trick of FFT, of which I will say nothing, all of these operations can be performed in a time that is proportional not to n square, but to n log n. And it makes a whole lot of a difference. It makes a difference between being a killing part of the code of being instead an almost negligible part of the code, or a manageable part of the code. So basically what one does, one starts from a reciprocal space representation of wave functions or charge densities, and one scatters. These are stored in memory in order of increasing magnitude of this reciprocal lattice vector. In order to do a Fourier transform, we have to scatter this onto a three-dimensional array identified by these P, Q, and S arguments. We do FFT. To go back, we do the inverse FFT, and to go back finally to the original representation, you do the inverse of scatter, that is a gather operation. Very last concept that I wish I could speak more about, but I will do this in private with you. Some very important concepts about Fourier analysis. Suppose you have a function that is a superposition of localized functions, like this, right? This function, of course, is periodic, because if you add an integer number to the argument, this would just shift the bell, the component of the sum that you would consider. Being periodic, this can be Fourier analyzed, and you will have that the Fourier transform of this periodic function is basically the discrete Fourier transform of this is basically related to the Fourier transform of the non-periodic function whose superposition gives rise to your periodic function. Pay attention. You have two functions here. You have a localized function, lowercase phi, whose repetition gives rise to a periodic function. What is the Fourier transform of the periodic function? The Fourier transform of the periodic function only exists for discrete reciprocal lattice vectors, whereas the Fourier transform of this localized function is defined for all the possible wave vectors. But for wave vectors that belong to this reciprocal lattice, the two Fourier transform basically coincide. Okay, simple concept. You have just to do by hands the Fourier transform of this and realize that because of periodicity and folding, the integral of the periodic function over a period is equal to the integral of the localized function over the entire space. This is the basic concept that allows you to map the Fourier coefficient of the periodic function onto the Fourier coefficient of the localized function. Now, a very important theorem that is known with the name of Nyquist. Actually, it seems that there is a huge story. It seems that Nyquist had little to do with the theorem. Actually, it was stated by Shannon, by the father of information theory, based on some prior work of Nyquist. But whoever has the paternity of the theorem is what allows you to listen to music on your MP3 machine, right? It's all about signal analysis and sampling of signals. Sounds complicated. Took me a while to understand, but it's trivial. I will make an effort to be understood in 30 seconds or 1 minute demonstration. Follow me if you can. Suppose you have a function that is different from 0 only on a finite interval, from minus a half and a half. 0 everywhere else. Okay? And now take the Fourier transform of this function. Suppose that you sample this Fourier transform at discrete points. Gosh. No, there is the picture doesn't show as it should. Suppose that you sample this wave function here at discrete points that are separated by delta q. And interpret these discrete points as a reciprocal lattice vector of a fake system. Right? A reciprocal lattice space of a fake system. So the inverse Fourier transform of this would be a periodic function, right? What would be the periodicity? The periodicity would be 2 pi over the distance between consecutive reciprocal lattice vectors, right? So if you take this delta q, this sampling rate, short enough, then 2 pi over delta q would be large. So the shorter the sampling time, the sampling rate, the larger the distance, the larger the period in direct space. If the period in direct space is larger than the support of the original function, then the interval over which the original function is different from 0, then by sampling the reciprocal space at the discrete values, you don't lose any information. You get the full information over the original function, because the periodic replica do not overlap. Very important concept. So you have this duality between direct and reciprocal space. You have that 2 pi over the distance between adjacent reciprocal vectors is equal to the direct space periodicity. If that periodicity is larger than the support of the function, you don't lose any information. That's why MP3 songs are of better quality when the files are larger, because the better the quality, the more faithful is the representation of the signal, and the more frequent has to be the sampling, right? So the more frequently you sample the sound, the more accurate would be the frequency representation of it. And if the sound was periodic, which it is not, of course, the song is not periodic, but if it was periodic, then by sampling the sound at a rate shorter than 2 pi over the period, you would have perfect sampling. Just you couldn't do any better. By increasing the sampling rate, you wouldn't do any better. Very important. If instead the sampling rate is too loose, then the distance between consecutive replica would be shorter than the support of the wave function, and you would lose information, because the form of the function that you reconstruct, in this case near the maximum, would be okay, but in between you would lose information. This loss of information is what is called technically aliasing error. This is what in the signal analysis literature is called the aliasing error. That is very important to us, because all the plane wave technology is all about the going back and forth from reciprocal and direct representation, direct space representation of wave functions or densities, and in order for this representation to be faithful, it is important that it is not affected by aliasing error. Very important. I'm afraid I have not been able I will not be able to go into the necessary details, but keep at least the concept that this is a very important thing to care about. Look into the slides that you will find in the website, and then let's discuss all together this issue in the next days. So back to molecules and materials. If you want to simulate a molecule, in this case must be water or something, for plane waves, what you actually do without knowing it is to simulate an array of water molecules that are periodically repeated. And here is this aliasing concept very important, of course, because it is important that the distance between consecutive molecules is larger than the support of the function that describe it. So the wave function and the density have to vanish at the border of this simulation cell. This is obvious, but strictly related with these aliasing concepts that I was describing before. Okay, let me skip this. For infinite crystals, the situation is more tricky, because periodicity is not fake, it is real. So you have a unit cell that repeats itself, so that you have the system is not periodic wave functions. So periodicity real space is for the density is real, but for the wave function the periodicity occurs over the entire crystal because of the von Karman boundary conditions, right? And you have to, in this case, you have to sample all the possible k points that form a quasi-continuum. So you have to sample all these discrete grid within a Brillouin zone. You use symmetry to reduce the sampling points to those that are independent of symmetry, and you can use tricks like shifts of the grid that I'm afraid I will not describe. I wish Shobran will. If she does not, somebody else will in the next few days. So I am done. Sorry again for the time it took to complete this presentation. This is the web address where you can download the copy of my slides. Thank you very much.